Methylene Blue, MB, helps against cancer cells that use glycolysis fermentation causing high levels of ROS rather than the usual pathway followed by healthy cells, respiration that produces less ROS. What about using the electron carrier Methylene Blue, MB, for prostate cancers?
Methylene Blue, MB, has shown potential in targeting cancer cells that rely heavily on glycolysis, the Warburg effect, and exhibit high levels of reactive oxygen species, ROS. Since prostate cancer cells often exhibit metabolic alterations, including increased glycolysis and ROS production, MB could theoretically be a promising therapeutic agent. Here's how MB might work in the context of prostate cancer. 1. Targeting glycolysis-dependent prostate cancer cells. Prostate cancer cells, especially in advanced or aggressive forms, often shift their metabolism to glycolysis, even in the presence of oxygen. This metabolic reprogramming leads to high ROS levels due to inefficient ATP production and mitochondrial dysfunction. MB, as an alternative electron carrier, can bypass dysfunctional mitochondrial electron transport chains and restore redox balance. This could selectively disrupt the energy production in cancer cells, leading to cell death, while sparing normal cells that rely on oxidative phosphorylation. 2. Redox modulation and ROS scavenging. MB has both pro-oxidant and antioxidant properties, depending on the context. In cancer cells with high ROS levels, MB can exacerbate oxidative stress, pushing the cells beyond their redox capacity and inducing apoptosis. In prostate cancer, where ROS levels are already elevated due to glycolytic metabolism, MB could further disrupt redox homeostasis, making it a potential therapeutic strategy. 3. Mitochondrial function restoration. MB, Methylene Blue, has the ability to partially restore mitochondrial activity by acting as an electron cycler. This means it can help improve the function of the electron transport chain, ETC, which is critical for energy production in cells. In prostate cancer cells with compromised mitochondria, MB can enhance the flow of electrons, reducing inefficiencies and electron leakage that lead to the production of reactive oxygen species, ROS. By doing so, MB may help the mitochondria generate energy more effectively, partially restoring their function. However, this restoration of mitochondrial activity can have a dual effect. If the mitochondrial damage in the cancer cells is too severe, the improved function may not be enough to fully rescue the cells. Instead, the restored activity could trigger apoptosis, programmed cell death. This is because mitochondria play a central role in regulating apoptosis. When mitochondrial function is severely impaired, the cell may already be on the brink of death. Restoring some activity could push the cell to recognize the extent of the damage and activate apoptotic pathways as a protective mechanism to eliminate dysfunctional cells. Thus, while MB can help improve mitochondrial function, it may also make the cells more susceptible to apoptosis, especially if the damage is too extensive to repair. 4. Synergy with existing therapies. MB could potentially enhance the efficacy of existing prostate cancer treatments, such as androgen deprivation therapy, ADT, or chemotherapy, by targeting the metabolic vulnerabilities of cancer cells. For example, combining MB with drugs that further increase ROS, e.g., certain chemotherapeutics, could lead to synergistic cancer cell killing. 5. Challenges and considerations. Selectivity. While MB may selectively target cancer cells due to their unique metabolic profile, its effects on normal cells, particularly at high doses, need to be carefully evaluated. Dosage and delivery. Optimal dosing and delivery methods, e.g., localized delivery to the prostate, would be critical to maximize efficacy and minimize off-target effects. Resistance. Prostate cancer cells may develop resistance to MB over time, especially if the treatment does not fully eradicate the cancer stem cell population. 6. Preclinical and clinical evidence. Preclinical studies have shown that MB can inhibit the growth of various cancer cell types, including those with glycolytic metabolism. However, specific studies on prostate cancer are limited. Clinical trials would be needed to evaluate the safety and efficacy of MB in prostate cancer patients, particularly in combination with standard therapies. Conclusion: Methylene Blue holds promise as a therapeutic agent for prostate cancer, particularly for tumors that rely on glycolysis and exhibit high ROS levels. Its ability to modulate redox balance and target metabolic vulnerabilities makes it an intriguing candidate for further research. However, more preclinical and clinical studies are needed to fully understand its potential and optimize its use in prostate cancer treatment.
Explain briefly for a high school student. MB, as an alternative electron carrier, can bypass dysfunctional mitochondrial electron transport chains and restore redox balance. What are MB properties regarding electrons? What is the electron transport chain used by mitochondria of cancerous cells? What is a redox balance in this context?
Sure. Let's break this down into simple terms. 1. What is methylene blue, MB, and its properties regarding electrons? Methylene blue, MB, is a molecule that can carry electrons. Think of it like a taxi for electrons. It can pick up electrons from one place and drop them off somewhere else. In cells, electrons are part of the process that generates energy. MB can step in and help move electrons when the normal system isn't working well. 2. What is the electron transport chain, ETC? The electron transport chain, ETC, is like a power line inside mitochondria, the energy factories of cells. It uses electrons to create energy, ATP, for the cell. In healthy cells, the ETC works smoothly, but in cancer cells, the ETC is often broken or not working well. Instead of using the ETC, cancer cells rely on a less efficient process called glycolysis, breaking down sugar without oxygen, to get energy. 3. What is a redox? Redox is short for reduction oxidation, which is just a fancy way of saying electron transfer. Reduction equals gaining electrons. Oxidation equals losing electrons. Redox reactions are happening all the time in cells to help produce energy and keep things balanced. 4. What is redox balance? Redox balance means having the right amount of electrons and molecules that carry them. If there are too many or too few electrons, it can cause problems, like too much stress on the cell, called oxidative stress. In cancer cells, the redox balance is often messed up because they produce a lot of reactive oxygen species, ROS, which are harmful molecules that can damage the cell. How MB helps? Since cancer cells have a broken ETC and too much ROS, MB can step in as an alternative electron carrier. It helps move electrons around, fixing the redox balance and reducing the harmful ROS. By doing this, MB can weaken cancer cells and make them more likely to die, while healthy cells, with a working ETC, are less affected. Summary: MB is like a taxi for electrons. Cancer cells have a broken power line, ETC, and too many harmful molecules, ROS. MB helps fix the electron balance, redox balance, in cancer cells, making them weaker and easier to target. Hope that makes sense. Let me know if you have more questions.
Fixing the redox balance and reducing the harmful ROS. By doing this, MB can weaken cancer cells and make them more likely to die. Cancer cells need high levels of ROS to survive. This is why they chose fermentation rather than oxidative phosphorylation, and MB helps kill them by forcing a redox balance that results in less ROS?
Great question. Let's clarify this. You're absolutely right that cancer cells often rely on high levels of ROS, reactive oxygen species, to survive and grow. However, this is a delicate balance. Too much ROS can be harmful even to cancer cells. Here's how methylene blue, MB, works in this context. 1. Cancer cells and ROS, a double-edged sword. Cancer cells produce a lot of ROS because they use fermentation, glycolysis, instead of the more efficient oxidative phosphorylation, which healthy cells use. This is called the Warburg effect. While cancer cells need some ROS to promote growth and survival, too much ROS can damage them and trigger cell death. Cancer cells are already living on the edge of this balance because they produce more ROS than healthy cells. 2. How MB disrupts this balance. MB acts as an electron carrier, helping to move electrons around in cells. When MB enters cancer cells, it can restore redox balance by reducing the excess ROS. This might sound counterintuitive. Why would reducing ROS kill cancer cells if they need ROS to survive? The key is that cancer cells depend on a specific level of ROS to survive. By forcing a redox balance, MB lowers ROS to a level that is too low for cancer cells to thrive, disrupting their survival mechanisms. Essentially, MB starves the cancer cells of the ROS they need to survive, pushing them towards cell death. 3. Why healthy cells are less affected. Healthy cells use oxidative phosphorylation, which produces much less ROS. They also have better systems to maintain redox balance. MB doesn't disrupt healthy cells as much because they don't rely on high ROS levels to survive. This makes MB potentially selective for cancer cells. Summary: cancer cells need high but controlled levels of ROS to survive. MB forces a redox balance that reduces ROS to a level that is too low for cancer cells, weakening them and making them more likely to die. Healthy cells, which don't rely on high ROS, are less affected by MB. So, yes, MB helps kill cancer cells by disrupting the delicate ROS balance. Let me know if you'd like further clarification.